We're going to continue in Chapter 12 by talking about ionic compounds. We'll start just by reviewing ions, which were covered in Chapter 5. So if you want a little more detail, go back and review Chapter 5. And then we'll talk about ionic bonding and how we predict the formulas when we know the ions. So as a review from Chapter 5, recall that ions are charged particles. And when we talk about charged particles, we can either talk about things that are positive, charges that are positive, or charges that are negative. Now, how the electrons are involved is when electrons are lost, remember their negative charge, that forms a positive ion. And when electrons are gained, remember their negative charge, that forms a negative ion. Now, one thing that I want you to remember is that metals tend to form the cations or the positive ions, and nonmetals tend to form the anions or the negative anions. The negative ions. And why I want you to think about that, because we've also discussed that ionic compounds are formed between metals and nonmetals. And so when we think a step further, we know that metals are cations, so they're positive charge. And nonmetals are anions, so they're negative charge, and we know that opposite charges attract. And so the attraction between the cations and the anions are what form the ionic bond. So let's recall how the pattern we get by predicting the charges of the representative, or what we call the main group elements, using the octet rule. Okay. So we're talking about main group, or also called representative. These are the tall columns that have the A with the number. And if we start on the left-hand side, these are the metals. They like to lose electrons. So we get a 1+, they lose their 1 valence electron. A 2+ for the alkaline earth metals. We go over here, we have 3+. We have 4+ or 4- if we were predicting. The truth is that zinc and lead are large atoms, and they can form a 4+ cation, but the nonmetals, which you would expect to form anions, are too small to hold the 4- charge. So in our class, that's not really something we're going to encounter. Some textbooks just leave that column blank, but I'm a pattern person. I don't want a blank one, so I just include it. And then 5A would be 3-. That now we're on the nonmetal side and they're gaining electrons. 6A is 2-. 7A, the halogens are 1-. And then the noble gases with a complete valence are very stable. They do not want to gain or lose electrons, so we do not predict charge for the noble gases. So that we're going to be using these charges in a little bit, and that is the pattern that we predicted in Chapter 5. Now, before we get to predicting the formulas for ionic compounds, let's take a little look at how losing and gaining electrons changes the size. So here we have an example of a sodium atom and a chlorine atom here on the right-hand side. And then on the left-hand side. And then on the right-hand side, they have gained and lost their electron. And so really what is happening is the electron from the sodium is being lost, but it's being transferred over to the chlorine atom. And so what you'll notice happens is when the atom loses an electron, the cation becomes smaller. And when an atom gains an electron, the ion is larger. And we call them, so this is a sodium ion, and it is smaller than the sodium atom. And then this is a chloride ion, and it is larger than the chlorine atom. Now you'll notice that the positive ions, or the cations, don't change name when you're naming the ion. But the anions, the negative ions, they take the stem, the beginning of the word, and change the ending to IDE. And so here, if we want to think visually what's happening, there is what we call the Lewis dot structure, which we learned previously. And this illustration here, they're using it to show how the electron is transferring or being lost and gained. This is an illustration which is drawn in colors and different things, shows it kind of getting bigger and smaller. I wouldn't ask you to draw it, but it might help you visualize what's happening. So what happens is an electron is transferred. That creates ions, and the ions are attracted to each other. So here you can see, and let me change my color of my pen. Here we have a sodium, which would have one valence electron, and they're showing you that this one valence electron is being transferred to the chlorine. So now if I look over onto the right-hand side here, the sodium is a positive charge because it lost an electron. And then the chloride ion, and they drew it in blue, that's not me, that it gained an electron, and so it becomes negative. Now both are happy because remember, with no dots, what's left underneath is the what they call core, which would be a valence electron, which would be a noble gas, very stable. And then the chloride ion now has 8 around it, which is also very stable. That's the octet. So I have asked before, on extra credit especially, to use Lewis dot structures. That's what we're doing here. Use Lewis dot structures to show the transfer of an electron. So I have asked students to do this before, sometimes on the exam, sometimes in an extra credit option. So I'd like you to pay a little attention to try to get a visual of understanding what's happening when the electron is transferred. Now, the result of this positive and negative attraction, we've mentioned this earlier, is a crystal lattice, or also known as a crystal array. It's this pattern of ions. The ions, if you think of them like little magnets, the positives are attracting the negatives, and then the ratio inside this crystal structure would be the same as the ratio in the formula unit. So if I see NaCl, this is 1 to 1, and inside the crystal is a 1 to 1 ratio. All 1 to 1 ratios would look similar. They'd have a similar pattern. But if you had 2 to 1 or 1 to 2, if the ratio was different, you'd still have a cluster, but it would have a different pattern. So a big thing that we're going to have to do in this chapter and then moving forward is write ionic formulas. Sometimes we write them from the name. Sometimes at this point we're just writing them from the elements. So we need to understand, how are we going to write a formula for an ionic compound? So you can see the first thing you need to do is you need to know what are the cations and the anions present. So we need to know what's the positive charge and what's the negative charge. We know that metals always form cations and nonmetals always form anions. So that can be helpful to us. Then we also have to consider what we're going to do is we're going to use the charges of the ions to make everything equal 0. So we need as many positives as we have negatives. So when I add them together, they equal 0. Okay. I think they call it like the principle of electrical neutrality, which sounds really fancy for just making everything equal 0. Now, when we write the formula, the metal is always going to come first. Okay, so metal first. Metal, then nonmetal. Okay, that's the convention. In the name and in the formula, it's always the positive ion, which is going to be the metal, followed by the negative ion, which is the nonmetal. And how we will show that we have more than one of each is we're going to use subscripts. Okay, and previously when we've talked about it, if there is no subscript, it just means it's 1. So these are some of the ideas outlining writing the formula. I think it's easier just to see, okay, how do we do it? So let's practice some, and then I have some more practice after this. So let's say I tell you, I'm going to start by giving you the ions. So let's say I said, let's put potassium and bromine together. So there they are, 2 of them. So what you do is you look, this is a +1 and this is a -1. So 1 and 1 would cancel to 0, and this would just be KBr. So I'd have 1 of each, because a +1 and a -1 together equals 0. Now I'm going to go ahead and teach you how to name these now. So ionic compounds, you literally just name the ions present. We know that metals are named the same as their element, and nonmetals change the N to IDE. So this is potassium bromide. So let's do another one. Let's say I had barium, which is a 2+, and oxygen, which is a 2-. So again, I look at the charges. That's what's going to determine what I have. And I say, okay, I have a 2+ and a 2-. Well, a 2+ and a 2- together without doing anything would equal 0. If in your calculator you said a +2 plus a -2, you would get 0. So this is also a 1-to-1 ratio. And I would name this barium oxide. These are the 2 ions. I have one more, and then I'm going to ask you a question. So let's say I have aluminum, and I want to put it with phosphorus, which is a 3-. So I look. This is a 3+. I wrote both of them as pluses. I'm sure you would have yelled at me. It's hard to get the eraser. I'm going to make it thinner. There we go. Sorry. So a 3+ and a 3-. So a 3+ and a 3- would cancel each other if you added them together, and it gets AlP, which is a weird thing looking, and it's aluminum. What do you think phosphorus would be? Yeah, it's phosphide. Kind of weird, too. Now, all 3 of these examples, I always start with this type of example, because what I want you to see is if the number on the positive charge is the same as the number on a negative charge, it's always a 1-to-1 ratio. So if the number on the positive is equal to the number on the negative, so 2+, 2-, 3+, 3-. If they're equal, it always results in a 1-to-1 ratio. Now, the reason I'm pointing this out is because I'm going to show you a little shortcut for when they're not equal to each other. Now, mathematically, we're using the idea that we want to have a number of each type of atom, so when I add their charges together, the total equals 0. That's the mathematical idea we're using. I'm going to show you a shortcut to getting that idea. Okay, so this time I'm going to start with, why don't I have magnesium? And I'm going to put it with chloride. And so when I look, they're not equal. So if I look, I have 2 positives. So to cancel 2 positives, I'm going to need 2 negatives. So I will need 2 chloride ions. And this would be called magnesium chloride. Now, even if it has 2 chloride ions, I don't really tell you it. I just say magnesium chloride. That's because ionic compounds, their formulas are based on their charges. So I don't have to tell you anything about them. Now, I want to add a little twist as we keep going. What if what was written was sodium? They put the elements. They said sodium with, I'm thinking sulfur. Now, how you would have to get the charges, if you're given the names of the elements, you go back to the periodic table. I'm going back in our notes. And you'd say, okay, sodium, you're a +1. And sulfur, you're a 2-. Whoops, sorry. So sodium is a +1. And sulfur is a 2-. So let's see, and this is the opposite of the above one. I have a +1, 2 negatives, so I'm going to need 2 of the positives. And I would name that sodium sulfide. Now, I'm going to show you a trick. Some people call it like the crossover method. It's not a trick. It's a shortcut. It's not a trick. And I find it helpful, especially when you're learning and doing those kind of things. So what you do is you look and you say, okay, how many magnesium do I need? You look at the opposite charge. So magnesium would need 1, and that's the number that would be here, but 1 we don't write. So it's a crossover. You look at the charge of the other element as long as they're not the same number, and that tells you quickly what you need. So then like I could say, okay, how many chloride ions do I need? I look here at the number 2, and see I wrote the 2 there. Now, I'm not flipping charges. I'm not shuffling charges. This really is just a quick shortcut to figure out, okay, how to make the numbers equal. And sometimes you can just look at it, and some people look at it more easily and just see it. But if you don't, you can use this little technique by looking at the opposite ion at what its charge value is. That tells you how many you need of the one you're looking at. So let's look at another one. So here I'd say sodium, and then you look at the opposite one. That's a 2. So see, it takes 2 sodium. And I'm not flipping the charges. Don't think that. And then here's sulfur, and I look over. That's a 1. So then I have a 1, which there's no number written. So what if I told you try this. What if I say aluminum and oxygen? Now, I want you to go back to if you have a periodic table to figure out the charges, I want you to figure out the charges and then figure out the formula. So you might want to pause it and figure out now, and then I'm going to keep going and I will give you the answer. So for aluminum and oxygen, I'd go back to my table and I'd say aluminum, you're a 3+. And oxygen is right behind sulfur. It's a 2-. So I have a 3+. and a 2 minus. Oops, I got excited with that. 2 minus. And then what I do, now think about it. If you didn't get that far, think about what formula you would write. So if I'm thinking mathematically, I would think aluminum is a 3 plus and oxygen's a 2 minus. The first number a 3 and a 2 have in common is 6. So it would take 2 of the aluminums to get up to 6, because 3 plus 3 is 6, and 3 of the oxygens to get up to 6, because 2 plus 2 plus 2 is 6. Or you could say aluminum, I'm going to need 2 of them. And then the oxygen, I'm going to need 3 of them. And that's how you get it. And this is called aluminum oxide. Now, I do have other videos in our Canvas shell that just have some more examples. They might have got these same ones. There's only so many ions that I can use when I'm doing this. So feel free to look at more of those. But I also have, I think, three practice slides so you can kind of practice. So let's look. So this is multiple choice, but I want you to try to figure it out. So it says, what is the formula for the compound formed from potassium and sulfur? So pause the video and try to get the answer, okay? And then I'm going to keep going, but you go ahead and pause and try. Okay, so potassium and sulfur. So they gave me the names, so I have to go back. Potassium is K and sulfur is S. Let's go look what their charges are. So potassium is right here, so it's a +1. And sulfur we've had before, it's a 2 negative. So a +1 and a 2 negative. Okay, so they're not equal to each other. So I know I can see it's going to take 2 potassium. But if you can't see it, do a shortcut. Potassium is going to take 2, which then it has to be letter C. And then sulfur is going to take 1. So we have K2S. So letter C. If you got letter C, you did it. Let's try another one. What is the formula for magnesium nitride? So again, pause and give yourself a try. All right, so magnesium, or give a try for yourself. I think I said it wrong. Okay, so magnesium is right here. It's a 2 plus. Nitride is right there. It's a 3 minus. So this is another example where 6 would be the lowest common number. And so you would need 3 of the magnesium and 2 of the nitrides to get it up to 6. But if you weren't uncertain of that, you could look and say, okay, magnesium, I need 3. And nitrogen, I need 2. So it would be Mg3N2, which again is letter C. All right, I have one more to practice. Then again, I have other videos you can practice, practice worksheet in your textbook. Just keep practicing these. Well, we're going to be using where you have to put the ions together and take them apart and put them back together when we do chemical reactions. So here's our last practice for this video, barium oxide. So you can pause and try it. So I still have to go back to my chart. Sorry for all the jumping. Barium is right here, so that's a 2 plus. Oxide is underneath. I'll erase so you can see. There it is. Oxide is underneath here. It's a 2 negative. So this is a 2 plus. and this is a 2 negative. And I hope you say, oh, they have the same number. And remember, when they have the same number, it's a 1-to-1 ratio, because a 2 plus cancels with a 2 minus without doing anything. So writing formulas for ionic compounds is actually a very useful thing. We encounter a lot of ionic compounds, and it's something that you should practice. So good luck practicing, and let me know if you have questions.